Welcome to the chunk Greedy Ensemble Selection. Greedy Ensemble Selection is a post-hoc method that is typically applied after AutoML systems produce a library of models. This library of model usually contains different algorithms trained with different hyperparameters, different seeds, and also different pre-processing choices. And many candidates are useful, and we can weight them. But we also would like to deploy all of them, and would like to have a weight vector that zeroes out a lot of these models. We could exhaustively optimize the subsets and then also the weights, but this is expensive and impractical. Greedy ensemble selection turns the search into a, greedy search. We obtain a trace, and that can be then turned into a final sparse ensemble. And we can see this as automated machine learning creates the library, and then greedy ensemble selection chooses which member should actually be in the ensemble in the end and should contribute to the final prediction. Greedy ensemble selection assumes a trained set of models and a validation set. The goal is to optimize a weighted averaging without continuous optimization. And it's a standard method in automated machine learning, as shown by Puruka et al. And it was introduced in 2004 by Rich Caruana and his colleagues, and they actually used it to select from 2,000 models produced by random search. And it works as follows. You start with an empty ensemble, and then one after the other, for each model that is in your library, you see what happens to my validation performance if I add this model. You then select the model that, when added to the ensemble, leads to the highest validation performance. And you then repeat this procedure until a budget is reached, and you return the best intermediate ensemble. So once you have one model in the ensemble, this is your new ensemble. And then in the second iteration, you see, if I add a second model in there, what is the validation performance? You basically simulate an ensemble of size 2. You simulate these for all ensembles that you can build with your library, and then again pick the model to add to the ensemble that, when added, gives the best validation score. This is what the pseudocode for this procedure would look like more formally. We as mentioned before, have base models as input, a validation set, and a budget, and the output are the weights of the different models. In line 3, we initialize several variables that we need for state tracking. So the counts of how often every model is used, then the current predictions as the score of the best model, and also the current best counts that we use in the end to return the best model at an intermediate step. Then we go over all t-budget steps from line 4 to 14. And in line 5 to 8, we actually figure out for one given ensemble which model would give the best performance if added. So we simulate adding a model and making the ensemble larger. Then in line 9, we pick the model that resulted in the best simulation and add it to the ensemble in line number 10. In lines 11 and 12, we check if it improved over the ensemble we had before, and if yes, we update the score of the best model and also update the counts. Then in the end, in line 15 and 16, we take the best ensemble that we had, and which is denoted by C star. These are the counts. And then for every model, we compute a weight, which is simply how often that model is included in the ensemble versus the amount of models in the ensemble at that point in time. And then we return this. This returns a sparse weight vector, as we will see in the next slides. This works really well in practice. Every greedy step is simple and fast. It is one matrix multiplication and addition, and followed by the computation of the validation score. This gives sparse ensembles because we only add also, members to the ensembles or models to the ensemble that actually improve the performance, and these in practice are only a few. A really great benefit of this method is that it can handle arbitrary performance metrics. So we can also handle metrics that cannot be that are not differentiable, such as the area under curve, which is really hard to actually approximate by a linear model, for example, or by even more advanced things like a neural network. And greedy ensemble selection is often competitive with more complex optimization schemes for ensembles. So let's have a look at a practical example. We use a random forest, a k-nearest neighbor, and a logistic regression. And the ensemble is empty, so all of them have a performance of 0. Then we simulate adding one model at a time. We start, well, the random forest gives 0.797, the k&n gives 0.841, and the logistic regression 0.737. So we pick the k&n because it results in the best ensemble. The next iteration, we see what happens if we add another model into the ensemble. And here, the random forest leads to the best performance, namely of 0.861. So we add that. And we go to the next iteration. And we see that adding the random forest again gives a good performance, improves performance most. And this is important to note. A model can be added multiple times and then the counter is increased. And this allows us to weight the models differently depending on how much they contribute to the validation performance. Then we check again which model to pick. And again, it is the random forest that we want to pick. It doesn't improve the performance further, but it gives the best performance, so we pick it. Then in the next iteration, the k&n again is the best method. So we again pick the k-nearest neighbor, which results in a performance of 0.905, which when we run this further actually turns out to be the best performance that we obtain. So we pick the first occurrence of this, which is an ensemble with 5 members, 3 times the k-nearest neighbor, and 2 times logistic regression, which gives us a weight vector of 60%, 40%, and 0% of the overall predictions. And now let's have a look at how the validation performance and test performance correlate or behave. So we can see here that actually greedy ensemble selection obtains the best overall performance. And unfortunately, the estimates are quite noisy, so this does not lead to the best overall performance. This was picking a single model, but actually this gives us quite good performance and improves over the other 2 ensemble methods. So again, this leads to us not having to select a single model, and works really well in case of having to select between multiple models. Now I want to discuss a few tricks of the trade that actually help us using ensemble selection as good as possible in practice. So always, instead of relying on a single validation set, use cross-validation as the validation score that we compute is much more reliable. If there are 2 models that perform the same, one should use a secondary metric, for example, the log loss for tie breaking. And when the library that we actually want to use is quite large, we actually should prune the number of models in the library to only include the top 50 to top 200 models, as suggested by the paper of Caruana, as this reduces the noise of which model to add. When using multiple model classes, one should keep at least the best model per class to increase the candidate diversity. And these insights that we should have sparse weights can also be applied to optimize weights with, for example, CMAES. To summarize what we have learned in this video, Greedy ensemble selection converts an AutoML model library into a sparse ensemble, and this library can be obtained by any procedure in the first place, for example, using a black box AutoML system, or using hyperparameter optimization, or even using the models obtained with manual search. It is metric agnostic and results in a sparse and practical weight vector that is really helpful for automated machine learning. And unfortunately, the weight optimization can overfit the validation data, so in the end, we need to check the test performance. Thank you very much, and see you in the next video.